Alright, how you doing? I'm going to try and go over this integral here for you, okay? But I've got my notes with me because, you know, this is not my normal day-to-day job sort of thing, okay? This is university level. And yeah, I don't want to keep on re-recording the video because I'm making a silly mistake. So I just thought I'd refer to notes every now and again just to make sure that it's proper, okay? And so I don't miss out any stuff as well because it's quite hard, you know, and I've got some notes here for when I need to give you some extra explanations and stuff, okay? So this is the integral, really great integral, okay? We're going to start off by saying let that equal to I, okay? And because of the limits here, you're trying to get a value for it, okay? We're not just trying to work out what the algebraic answer to it is, we're trying to get what the value is, okay? Because it's an area under a curve, effectively, that's what we're looking for, okay? So what we're saying is this is actually the same as if we did this, okay? So integral between negative infinity and positive infinity of e to the negative y squared, and we can choose any letter we want. That's the reason why we choose y. Okay, choose any letter you want, but that's the same. You can have e to the negative t squared dt, e to the negative, you know, whatever letter you choose, okay? Because they're both the same, because we're substituting limits in, you see, and get an actual answer, okay? So the method of trying to work out this integral is to combine these, okay? And initially we're going to multiply them together. We're going to say that I squared, okay, is going to be equal to just that times that, all right? So if we write it out, you're going to have negative infinity to positive infinity of e to the negative x squared dx, and then multiply that by negative infinity to positive infinity e to the negative y squared dy. Okay, so yeah, that's not terribly difficult. It's just the method we're going to use. Okay, right. The next bit. Okay, I'm just going to check my notes, see which order I do this in. Okay, yeah. Okay, so what you can do with this is you can just rewrite it like this, you see. So integral between negative infinity and positive infinity. I've forgotten it again, you see. Because I want to try and get it right, okay. Of this integral between negative infinity, that's the most awful infinity sign that I've done. Negative infinity to positive infinity, okay. Of e to the, I want to get it right, negative x squared, e to the negative y squared, dx dy. Well, now why is that the same? Okay. Basically, it's about the dx's and the dy's. Okay. If you're integrating with respect to y, the x's you can treat like constants. Okay. Just as if you integrate with respect to x, the y's you can treat like constants as well. Okay. So what we can do is we can just write it like this. I've put brackets. You won't often see brackets, but I think they help, okay? Because really what you're doing is you're integrating this bit first, okay? Let me just take away the brackets, you see. It's not obvious what you're doing there, is it? It kind of looks like you're just doing this times this times this times this times this times this, but that's not it. That's mathematically not what's happening, okay? You're finding this integral first, okay? You're integrating that with respect to x, all right? And then once you're done with that, you're integrating that answer with respect to y. That's what it actually means. Okay, it's called a double integral. Okay, and yes, there are such things as triple integrals. Yeah, it's kind of cool. Okay, why is it called a double integral? I might forget to mention later, but it's to do with finding areas. Okay, and why do you have triple integrals? It's to do with finding volumes. Okay. Which might not make too much sense, but I just wanted to try and give you a little bit of something, okay? So no, I do need a lot of board space for this, okay? So I'm gonna just go back to the top again, okay? We know what the question is, so there's no harm in rubbing that out, is there? Okay? So let's just remind ourselves, that is I squared, isn't it? Okay, so you've got I squared, and then that's equal to, right, we're gonna sort this out, okay? I think I know what's coming next. I just want to check. Yeah, that's right. So, integral between negative and positive infinity. And I don't need the brackets. Do you mind if I don't write brackets? Because you wouldn't normally write the brackets in, you see. Negative to positive infinity again. and e to the negative x squared plus y squared dx dy. Okay, I'm not going to rub this out now, okay? Right. And now we're going to venture into polar coordinates, which is jolly exciting, isn't it? You might not have seen polar coordinates before. Let me just explain to you what polar coordinates is all about. Okay? Different colour pen time. Okay? Cartesian coordinates are when you've got a point and that point is referenced about the origin. We call that origin. And the way we reference it is the translation horizontally and vertically. All right? So the coordinate point 3, 4 in Cartesian coordinates will be from the origin 3 to the right 4 upwards. That's Cartesian coordinates, named after one of my favourite mathematicians, René Descartes. I think, therefore, I am all of that. Okay? That's Cartesian coordinates. Polar coordinates are something different. Okay? Polar coordinates, you have an initial line, it's called. So you might see polar coordinates mentioned like that, okay? Let me just write that down for you. That's called an initial line. It's not called an x-axis or horizontal axis or even an axis. It's called an initial line, okay? But it's a bit like the x-axis, okay? And it's got not the origin, it's called the pole. Yeah, it's called the pole, okay? In Cartesian coordinates, you plot a point like that and you reference it horizontally and vertically, as I said. How do you do it in polar coordinates? Well, in polar coordinates, what we do is we look at what the distance is from here to here, sometimes called the modulus, okay? And we look at what the angle is. That distance from the origin, I've done it on the pole, to that point there, we call r, all right? And that angle we call theta. So that coordinate point we'd mark as r theta. See, I don't need my notes for this. This is my comfort zone because I teach this kind of regularly, well, once a year. Okay. So we call that coordinate point r theta, where r represents the length and r represents the angle it makes with the pole. Okay. Incidentally, angles are always, I'm sure you know this, angles are always in an anti-clockwise direction, no matter which system you're using, Cartesian coordinates or polar coordinates. Okay. So, what does that mean? Okay, what does that mean? So, if you have the coordinate point, let's say 2 pi over 4, always radians. Okay, always radians. Okay. Particularly when you've got calculus involved as well. Don't forget. Okay. What that means is, if this is the initial line, there, mark it L. Then pi over 4. Always do the angle first. Okay, because I know it doesn't make sense because the angle comes afterwards. You've got the r and then the theta, okay? But always do the angle first. So the angle is going to be pi over 4, isn't it? So that's an angle of pi over 4. And then you just measure out 2 units from the origin. Okay, and that's the coordinate point 2 pi over 4. Okay, and that's polar coordinates, it's as simple as that. Okay, so if I change that to 12 pi over 4, I'll just extend the line. Yeah, if I changed it instead to 3 pi over 4, it'd end up like that, but the same length, don't forget, okay? There's a lot of crossover work between this and vectors, yeah? Because vectors are all about direction, it's all about modulus as well. That's why I purposely call that the modulus. There's also a lot of crossover with this with complex numbers. Okay, as soon as you get into all this, you suddenly see a lot of maths really coming together. Complex numbers, vectors, and this, okay? So it's really fascinating. It's a really good one to research as well. Okay, now, I'll go a little bit off topic because it's really kind of fascinating. Sometimes the challenge is trying to convert between polar coordinates and Cartesian coordinates. Okay. Well, suppose you've got this coordinate here and polar coordinates is 2 pi over 4, but you're thinking, I want to have that in Cartesian coordinates. Well, what are you going to do? So let's just do it here. No, let's do it here. Sorry, change your mind. What are you going to do? Okay. What we'll do is we'll just drop a perpendicular line to the initial line. Can you see what we do now? Okay. Yeah, we use trigonometry. Okay. Because this length here, call it the hypotenuse, of course, is 2. Okay, and so if you want to work out what that is, the horizontal distance for our x coordinate, that's going to be 2 cos pi over 4. Isn't it? And what is cosine pi over 4? It's root 2 over 2. So that's just going to be root 2. Right? And then this here, what's that going to be? That's going to be 2 sine pi over 4. Yeah, sine pi over 4 is the same, isn't it? So that's also going to be root 2. Okay, if I just fit it on. Okay, so that means is in Cartesian coordinates, it will be root 2, root 2. You can check that using Pythagoras' theorem, of course. That squared plus that squared equals that squared. Okay, so you see how that works? Okay, why are polar coordinates useful? Well, because sometimes it helps us to draw interesting curves. Okay, so for example, here, let's just get an interesting example up. So I'm going to go to this whiteboard now. Okay, for example, if you have the polar equation, oh no, stuck now. Let's just go for that. R equals theta. Okay. You can actually draw it out and see what it is. Okay. Well, when theta equals 0, r equals 0. So angle 0, radius 0. When theta equals, say, pi over 2, there, r is equal to pi over 2. That's not the point. When theta, try again. When theta equals pi over 4, r equals pi over 4. Yeah. When theta equals pi over 2, 90 degrees, r gets bigger, can you see? When theta equals, let's just say pi, measured out here, r equals pi. Can you see what's happening? Okay, the actual curve is going to look like this. It keeps on going, spiralling out. Okay, it's called an Archimedean spiral. Okay, there's no way you can do that with Cartesian coordinates, you see. But a spiral is such a lovely graph, isn't it? Okay, so, and there's more you can actually research on that. Okay, that's generally an equation of the form I equals a theta, where a is any number. Okay, so you can look at. There's also some really other cool stuff as well. Okay, maybe something you want to research. Okay, but here is an interesting curve that you can actually draw. Okay, so there's the initial line. So let's just draw one in. That's called a cardioid. A cardioid. Okay, you can look up the equation for that if you want. Okay. Let's turn it round. No, I love maths. It's cool stuff. Okay, so yeah, polar coordinates is pretty useful. Okay, but you know, getting back to this. Okay, suppose you've got the general coordinate r theta, and you want to convert that into Cartesian coordinates, doing the same thing. Well, look, it's quite simple. Okay, what you do, just drop a perpendicular, of course. Yeah. You can work out that is. Okay, that's going to be r cos theta, isn't it? Yeah, let's just write that in. R cos theta. And work out that is. That's just going to be r sine theta. Yeah. But if we now call that our x coordinate, as in that distance there is x. If we call that our y coordinate, that distance is y. Get an expression between x, y and r for me. That squared plus that squared equals r squared, because it's a right angled triangle. Yeah. And that gives us our important result, r squared equals x squared plus y squared. There. Right. So knowing polar coordinates is kind of useful, kind of helpful. Okay. I just want to check it's recording because I've done a couple of these and they've stopped. I'm like, oh, great. I'm glad it's recorded. I hope you're still with me as well. Right, I'm going to rub off all of this. Okay. This is the sort of question where I could do with 2 really big boards in my classroom to actually do it. Because it's kind of nice to refer back to it. I can say, you know, go back to this or go back to that or go back to, you know, I'm having to rub it all off, okay? So, right, because of that then, can you remember that? I'm sure you can remember that. Okay. What we can do is just rewrite that, can't we? We can rewrite that as, for the moment anyway, integral between this and this, this and this, e to the negative r squared. yeah? Then what you're going to do with the dx, dy? You can't really integrate that now with respect to x and y, because r is a variable, okay? You've got to have this in terms of something else, dr, or d theta, at least a dr, haven't you? Now you've got to use the polar coordinates to convert that as well, okay? That's where the next part of my explanation is coming up, okay? Yeah. Oh, I've rubbed it all off. Never mind. Never mind, I'll do it. Right. Cartesian coordinates. Okay. What are you going to do to work out an area under a curve? Okay. Which is a bit like trapezium rule. Okay, really. What you can do is you can split it up into tiny rectangles, like that. Okay. And what you can do is work out what the width times the length is, length times width. Okay. If delta x represents a small change in horizontal distance, delta y represents a small change in vertical distance, you can work out there. That's effectively what integration is. It's an infinite summation of rectangles bounded between a curve and the x-axis in Cartesian coordinates. Okay, that's that. That's for Cartesian coordinates. Okay, so look, when we do the dx dy, that's why it gives you an area. Okay, and that's why, hopefully if you do this at university, the double integrals with a dx and a dy, that's to make some area calculations easier. Okay, what's happening with polar coordinates? Okay, now, despite what I said, sorry, I want to put some notes to the side of that. Despite what I said, okay, about the initial line, yeah, we sometimes, well, I quite often do a vertical line as well, because it's easier. Let's face it, it's easier, because we're often using angles and stuff, and it's just nice to have a point of reference. Okay, so yeah, sometimes that initial line is called the line theta equals 0, because that's when the angle is 0, and that is called when theta equals pi over 2. And then, yeah, we don't do that. That would be theta is 3 pi over 2, and that would be, sorry, theta equals pi, and that would be 3 pi over 2, and that would be 2 pi. Okay. Right, with polar coordinates, okay, what you're doing is, well, do you remember this I showed you? Yeah, that's normally an equation in terms of r and theta, and so what you're often doing is you're integrating with respect to theta. The limits you often use are between theta is this and theta is this. Okay, so let me give you an example. Okay, yeah, use this one. If you wanted to work out the area of this curve bounded between this line and this line, let me just shade it in for you. You'd need to know what the value of theta was there and what the value of theta was there. Okay, and in your integration you'd substitute in the two different values of theta, you see, and have your equation in terms of r and a b to theta. That's what you're often doing with polar coordinates. Right? But because you need to use theta's limits, it's like a spiralling area you're trying to calculate. Does that make sense? Okay. See, this is like you're doing, it's called a sweeping area between here and here. That's what you're doing. As you increase the value of theta from here to here, you work out the area that's swept out between those and the actual curve. Right? In general, what you're doing is this. Okay. You've got a value of theta here and the value of theta here, and you're working out that area. So it's not rectangles at all. Cartesian coordinates, they're rectangular. Polar coordinates, they're sectors of circles. Okay, they're sectors of circles. Okay. Right. I want to just focus on this area here. All right. Now, we tend to use delta x as a small change in x. I'm going to use delta theta to represent a small change in angle. Okay, so what that means is between here and here, there's a small change in what the angle actually is. I'm going to use delta r to represent a small change in that value of r. Okay. maybe you can understand why we use r now in polar coordinates, because it's more like a radius, isn't it? Okay. Let me just label this r here. Okay. You're going to see it doesn't really matter whether r represents that or r represents that. You're going to see why. Okay. It's just generically r is what the radius of the circle is. Okay. We're interested in what the area shaded in is. Okay. So area shaded in. Okay. And we're going to approximate it. Okay. We're going to approximate it. That is roughly a rectangle, isn't it? Roughly a rectangle. I just need to denote a length for this. We usually use S to represent arc length. Okay, arc length. Right. So the area of that is approximately going to be S times delta R. Yeah. So approximately this times this. That's approximately a rectangle. Okay. Do you remember what the formula for an arc length is? In radians, of course. Yeah. Arc length's r theta, isn't it? Fantastic. We use r and theta. Yeah. These letters aren't chosen at random, you know. We use them for a very good reason. Okay. So in this, it's going to be what? R times d theta, because I've used d theta as the angle. So r delta theta. Okay. So did I say d theta? I didn't mean to slip because of what's coming soon. Okay. Because sometimes we're going to change these deltas to d's. Yeah. So what that means is the area that's shaded is approximately equal to, what's that? Well, the arc length S, okay, multiplied by delta R. Yeah, this bit there. The arc length times by delta R. I've just said the arc length is this, R delta theta. So that's S times by another delta R. Some bits starting to make sense now. I can see there's a clicking. It's like, oh, I kind of felt it. Yeah, I kind of felt it. It's kind of cool, isn't it? This is the really good bit. I really love this bit. It's like really great. A lot of maths works when you do this, including calculus, integration and differentiation. As delta theta, delta r tends towards 0. Lovely, isn't it? Okay. Right, if you're doing this in a lecture at university, they'd probably be using limits. Okay, so this is not a strict, thorough proof. Please don't post this. Okay, it's just an explanation. Okay, what's happening as delta theta, delta r tends towards 0? We start to use d's instead, but also this approximation becomes an equals, because at 0, this shape here can be modelled as exactly the same as a rectangle. Okay, so what that means is the area is going to become, here we are, r d theta dr. So what that means is here, the dx times dy rectangular area, okay, is going to become r d theta dr. Is that okay? Yeah, I just need to refer to my notes just a little bit, because there's something I need to include, which I've not put in yet. Yeah. Now, remember what I said earlier about the bracketed bit? Yeah. What this integral means is, really, you do that integral in the brackets first, and then this. Yeah. Now, in terms of integrating with respect to r as a line, as a length, extends between negative and positive infinity. Okay. Theta, however, when you integrate with respect to theta, that's not a length, that's an angle. And in polar coordinates, that goes from theta 0 all the way round to 2 pi. Okay. So these limits need to swap, need to change between 0 and 2 pi. Okay, so I'm hoping that makes a lot of sense. Okay, so there's a lot of stuff going on there. So I was checking it's still recording, because I'd be so annoyed if I had to do that all over again. Well, no, not annoyed. You know what I mean. This is nice. Okay, how am I doing? This is only the second time I've ever gone over this. Okay, the first time was 3 years ago. on the board. I have my notes right in front of me, and the second time is today. Okay. Here we go. It's a lovely bit of maths though. It really is. So we've got that. Okay. I just want to check to see if I've got any more points to make. No, the only points I made in my, which I think would be useful for you, I suppose, if you're taking notes on this, is oh, I made a small error. Small, okay. The value of r between 0, okay. So if I get this back up again, okay. Well, I'm not going to do the video again just because I didn't do that right. Okay, you can forgive the small little slip, can't you? That's a good job. I've got one note to see. See, r, you see, is like, that's a value of r, that's a value of r. We don't generally go from negative infinity. I should have spotted that really. Please don't tell anyone. Yeah, so r is between 0 and, because, yeah, well, you could have probably thought of a reason why. I mean, because it's, that's what Pythagoras' theorem. You know, it's a length, you don't have a negative length, okay, so, you know, yeah, it can't be perfect, okay, it's just a slip, really. So yeah, between 0 and infinity, so it's a good odd job I'm reading this, okay. So maybe when you're writing this, you write down notes. Those are the limits for r, yeah. These are the limits for theta. Remember, it's important that when you are integrating, you know what limits you're using and which variable you're using them for, okay. Just want to check that there's anything else that I need. No, that's all fine. We're all good. Okay. Right. So, what will we do next? Okay. Well, I'm now going to take this inner bracket integral. Okay. So between 0 and 2 pi of e to the negative r squared r d theta. Okay. I'm now going to take that. And then once we've got that, we'll look at the outer integral, okay? Because remember, that's what the brackets are. The brackets are so important, okay? This is with respect to theta. Now, in terms of this here, that's not in terms of theta, is it? So you can actually write it like this: e to the negative r squared times r. Should we put the r there? Yeah, let's put the r there. It's nice, isn't it? Between 0 and 2 pi of d theta. Same thing. Remember, I can do that with any constant, just take it outside. Okay, the bracket. And integral of 1 then, d theta, it's just theta, isn't it? So you get r e to the negative r squared, and then you get theta, and then between 0 and 2 pi are the limits. Okay, and theta is 0, 0 of course, so 2 pi. So you have 2 pi r e to the negative r squared. So what that means is the bit in brackets is going to be 2 pi r e to the negative r squared. You go with that? Good. I'm glad you said yes. This now, let's do this. Very important. I don't rub that out because what we're doing here is just the integral squared, isn't it? Because right at the end, to work out what our integral is, we're going to want to square root that. I kind of wish I didn't rub that bit out, but I did. So I'm going to make sure I get my notes back again so I don't skip that, okay? So what did I have? So I had integral between 0 and infinity of, and we worked out this here, didn't we? That was 2 pi r e to the negative r squared, and then dr was at the end, yeah? Yeah, good. It's nicer, in a way, to write it like this, 2 pi, integral between 0 and infinity of r e to the negative r squared dr. That's an inspection question. Okay. Why is it an inspection question? Well, because, you know, if you've got y equals e to the negative r squared, then dy dr is going to equal to the same, e to the negative r squared multiplied by negative 2r. Yeah, what you're spotting is like the r squared differentiated, you get r in comparison to everything you've been doing. That's a bit simple, isn't it? Okay, so what does this mean that this is going to become? Okay, so if I half that, so divide that by 2, I'm going to half that, okay? And so I'm going to end up with, yeah, that negative r e to the negative r squared, but that's not negative, is it? So I'll just multiply it by -1. So get this, negative half e to the negative r squared. Okay. So that's going to be equal to 2 pi, let's not forget we're going to have put the limits in as well, negative a half e to the negative r squared. You might think, oh, I don't like that, the negative is going to make it a bit awkward. But no, it works out nicely in the end. Let's put limits in, 0, infinity. Because we're going to have 2 pi, and then let's just work this out. What happens to this as r tends towards infinity? It becomes 0, doesn't it? Okay, and then you're subtracting, great. Negative a half, so plus a half e to the power of 0, which is 1. Okay, 2 pi times a half is just pi. That's just so fantastic. Sorry for the high voice, I went a bit, yeah. That's just so fantastic. That's just so great, isn't it? It's just, yeah, I squared, the whole integral is equal to pi. What an amazing number pi is. It's still not as good as e. E is still the best number. But yeah, it's just, that always blows me away. Okay? So the integral, don't forget, I is equal to root pi, which is kind of a lovely answer. Yeah, but it's kind of nice. So there you go. Yeah, that's your solution. Okay. Maybe some more, I don't know, not extension work, but research work is how is that related to the normal curve in probability? You know what I mean? There we go. It's not a bad normal curve, is it? Okay. How is that related to the normal curve in probability? Come on, research, it'll blow your mind away again. Okay, but yeah, it's kind of linked together. Okay. Alright, hope you enjoy that. See you later.